Okay, so we have another couple interesting equations here for us to solve. So this requires us to really know the exponent laws very, very well. So we've got 3 to the x plus 5 minus 3 to the x equals 100. I could break this apart using exponent laws, sort of the reverse of what we're used to. And we could say that's 3 to the x times 3 to the 5 minus 3 to the x equals 100. Because when you multiply powers together, you add the exponents. And then now I can just factor out the 3 to the x. Then I can divide both sides by 3 to the 5 minus 1. And then I can work this out, so that becomes 100 over 242. Now I can take the log of both sides, so I get x log 3 equals 100 over 242, sorry, the log of that. And then x is the log of 100 over 242 all over the log of 3. And then when you work all that out, x equals negative 0.8044. Now on to this one. Again, we have to really know the exponent law as well. So I see I've got a 2 to the x here. I've got 3 terms. There's a constant here, then there's a couple terms with variables. So being clever, I'm sure you would notice that this can be turned around to say 2 to the x all squared minus 7 times 2 to the x minus 8 equals 0. And Viola, as the French say, we now have a quadratic. So now we can just use sum across products to factor this. So suppose this is something like x squared minus 7x minus 8. We could solve this, so that would give 2 to the x minus 8 times 2 to the x plus 1. Because 2 to the x times 2 to the x gives us 2 to the x squared. 2 to the x times 1 minus 8 times 2 to the x gives us negative 7 times 2 to the x, and then negative 8 times positive 1 gives us negative 8. And now if two factors equal 0 when they're multiplied together, then obviously either one equals 0 or the other one equals 0. And then we can just rearrange this, get a common base, and x equals 3. Now on this side do the same thing. Now we have a bit of a problem though. What could you raise the base 2 to give you a negative 1? Nothing. This is undefined. So our only solution here is x equals 3. Okay, so now let's move along to compound interest and exponential growth and decay formulas. They're basically the same thing, just one version is fancier than the other. So for compound interest, we've got A, the final amount, equals P, which is the principal amount invested, multiplied by 1 plus I, which is the interest rate per compounding period, to the exponent n, which is the number of compounding periods. And then for the exponential growth and decay, we've got some initial value. The final amount is n. The principal amount, or the initial amount, is c. A is the growth or decay factor. And then we've got the exponent of 2 over w. W is the growth or decay period, or the half-life if we actually end up having a half-life problem. And t is the observation time. And the t and the w must be in the same units. If you're talking about years, they both must be years. Days, they must be days, etc., etc. Alright, so let's take a look at one of the examples here. Marcus invests $5,000 at 6% per annum, compounded quarterly. How many years will it take for his investment to triple in value? Okay, so if his investment's tripling in value, what would it become? Correct, that would be $15,000 of his initial $5,000 investment. And it's 6% per annum, but compounded quarterly. So 6% is 0.06 as a decimal. And if it's compounded quarterly, and now that's per year, but if it's compounded quarterly, we have to divide by 4, because it wouldn't get 6% every 3 months. They would only get 6% every year, which means that they would get 1.5% every 3 months. And we want to find out how many years that's going to be. So for the n here in this case, because it's compounded quarterly, we're going to multiply this by n because we want to see how many years it is. So we're going to multiply that by 4 to get the total number of compounding periods, and then we'll do one final calculation at the end to get the number of years. So inside the brackets now we've got 1 plus 0.015 all to the exponent 4n, or 4t, or whatever you like to do. Now we'll just start rearranging this to solve for n. So we divide both sides by 5,000. So we get 3 equals 1 plus 0.015 to the 4n. And so then, because we need the exponent, I'm going to take the log of both sides. So I'm going to take the log of 3, and I'll bring that exponent down in front. 4n log of 1.015 as I add the two values together in the brackets. Divide both sides by log of 1.015, so I've got 4n equals log of 3 over the log of 1.015. And so 4n equals, please do that calculation, 73.78876. And then, so that's the number of compounding periods. So we divide both sides by 4. And so that's 18.447. So I would say n is approximately 18.5 years. And then of course with all word problems, we'll have a little therefore statement. Therefore, Marcus blah blah blah, 18.5 years, yada yada yada. Okay, moving right along here. Plutonium, very dangerous. I wouldn't suggest you buying this and doing any experiments with this at home. Plutonium-239 has a half-life of 24,000 years. So chances are you wouldn't be around to see half of it disappear. So you might want to be careful of that stuff. We want to find out how long it is until 70% of the initial amount remains. Okay, so we use the exponential growth and decay formula for this. So we want the final amount, and so the final amount is going to be 70%. So we got 70. So the initial amount, well, we don't know what that is, but I imagine it'll be all of what you buy, so that would be 100%. And it's a half-life, so the growth or decay factor, in this case is the decay factor, is a half. And we want to know how long it's going to be until 70% remains, so we need to find the t, and the half-life is 24,000. Okay, so we'll just do a little bit of rearranging here. So divide both sides by 100, so we get 0.7 equals 1/2 to the t over 24,000. I'll take the log of both sides because I want to find what the exponent is. So the log of 0.7, and then I'll bring this down in front using logarithm laws. I'll divide both sides by log of a half. This time I'll just use a decimal there. Equals t over 24,000. I want to find what t is, so I'll say t equals, and so that's because t is being divided by 24,000, I'll multiply both sides by 24,000. So I get 24,000 times log of 0.7 over log of 0.5. Remember to do the log of 0.7 independently from doing the log of 0.5 and dividing those responses. So let's take a look to see what that gives us. And by my calculations, I've got 12,349.76 years. So therefore, it takes blah 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 approximately 12,300 and let's say 50 years, yada yada yada, until 70% remains.